Good morning students, myself Vaidegi working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject Analog IC Design for the 6th semester students. In this lecture we will see about the single stage amplifiers in analog IC design. We will focus on three fundamental topologies: the common source, common gate and source follower. These are the building blocks of more complex analog circuits. First we see about the fundamentals. Single stage amplifiers matter because they form the foundation of analog design. Every complex IC you encounter, whether in communication systems, sensors or processors, relies on these basic amplifier stages. They amplify weak signals, buffer them or drive loads. By mastering these, you will unlock the ability to design multi-stage and feedback systems. Next we see about the amplifier performance essentials. When evaluating amplifier performance, four parameters are critical: gain, impedance, bandwidth and noise. Small signal gain tells us how effectively the amplifier boosts signals. Input and output impedance determine how well it interfaces with other stages. Bandwidth is always a trade-off with gain. And of course, noise and linearity decide how clean and distortion-free your signal remains. Next we see about the common source amplifier basics. The common source amplifier is the most popular topology. Input goes to the gate, output is taken from the drain and the source is grounded. It provides high voltage gain but introduces a 180-degree phase inversion. This inversion is important when cascading multiple stages. Next we see about the common source amplifier. The small signal model uses transconductance GM and output resistance R0. These two parameters are largely defined gain. The load choice is crucial. Resistive loads are simple but waste headroom. Current source loads maximize gain and source degeneration improves linearity and bandwidth at the cost of gain. Next we see about the common gate amplifier. The common gate amplifier takes input as a source with the gate held at AC ground. Output is at the drain. It has low input impedance and high output impedance, making it excellent for current buffering. Unlike CS amplifier, there is no phase inversion, and because it reduces the Miller effect, it performs well at high frequencies and ideal for RF front ends and wideband systems. Next we see about the source follower. The source follower is also called the common drain amplifier and is essentially a unity gain buffer. Input at the gate, output at the source and drain tied to the supply. Its strength lies in impedance transformation, very high input impedance and very low output impedance. This makes it perfect for buffering between stages without losing signal amplitude. Next we see about the comparative summary of the common source versus common gate and the source follower. Let's compare. The common source amplifier gives the highest gain but inverts phase. The common gate amplifier offers moderate gain, no inversion and shines in RF applications. The source follower provides unity gain, no inversion and excellent buffering. So choose common source for amplification, common gate for high frequency or current applications and source follower when impedance matching is needed. Next we see about the practical design considerations. In real world design, transistor sizing and biasing are critical. Larger devices increases transconductance but also parasitic capacitance. Short channel effects in modern CMOS reduce R0 and introduce velocity saturation. Noise and distortion must be balanced against power consumption. And in deep submicron technologies, challenges like reduced supply voltages and leakage demand careful layout matching. Finally, we came to the summary of this lecture. To conclude, single stage amplifiers are the cornerstone of analog IC design. By understanding CS, CG, and CSF, you build the intuition needed for the advanced circuits like cascodes and feedback systems. For deeper study, I recommend Zawi's design of analog CMOS integrated circuits. Hope you all understood. We will see in the next lecture. Thank you.